Now let's go over the quiz question that we had asked last week. So we had a virtual memory system which used paging and that would support virtual memory of 2 to the power 40 bytes. Okay. And in the system, we said that the page table of a process takes up to X bytes. And we said that we have a newer version and the virtual address space in the physical memory is doubled. Then the question is, what would be the change in the size of the page table? Now in this question I forgot to mention that there's this missing information that the page size, we can assume that it's 2 to the power s bytes. Okay. Now when we talk about the size of the page table, this is essentially it's the multiplication of the number of page table entries in the table times the size of the page table entry in bytes. Okay. So in this current system, we said that X was the size of the page table. Now, how many page table entries do we have in this particular system? Well, the virtual address has 40 bits, okay? And since the page size is 2 to the power s, it means that the page offset uses s bits of them. And so as a result, the number of page table entries in the page table is 2 to the power 40 minus s. Okay. And then comes the size of the page table entry in bytes. So if we assume that this is like this indicates the size of the page table entry in bits, and if we divide it by 8 then we'll get its size. So from the information we say that x equals 2 to the power 40 minus s times the size of PTE in bytes, and we split it by divided by 8. Now when we double the virtual memory system, then automatically the number of the page table entries doubles. Okay, that's because instead of 2 to the power, like when we have doubling virtual memory means that, let's say that here we have the, okay, let's see, here we have the virtual address, okay, which is 40 bits, and we split this into this is offset. So here we have 8, no, sorry, s bits for offset, okay. And here we use for VPN, we use 40 minus 1. Now when we double virtual memory, it means that I'm adding one more bit here. Okay, so now the VPN is 40 minus s. Now this should be actually 41 minus s. Okay, and as a result the size of our page table doubles because we use 41 minus s bits to index the page table. And then we also said that the physical memory also doubled. Now what does it mean? In the case of the physical address, let's say that the physical address was like this. So we had s bits for offset, and then we had the ppn here. Okay, so we don't know how many it consumes, but doubling pm, the physical memory, means that I need to have one extra bit here as part of my ppn. Now this would grow the size of page table entry by 1 bit, or by 1/8 bytes. Okay, so when we look at this, now the size of the new page table I can compute it as such. So let me just look at it here. So let's call the size of new PT as x prime, and now this is 2 to the power 40 minus s. This was how many, this was the size of the page table entries in the previous case. I multiplied it by 2 because the VM was doubled. Okay, and then I multiply this with the size of the page table entry. So it's effectively page table entry, the size of it in terms of bits, plus 1 divided by 8. And as a result, if you do the multiplication, this remains the same, and we split that into 2. Okay, now when you do the multiplication, you can realize that this portion, this term, equals to x. Okay, and when we do the rest of the multiplication, then we end up seeing that x prime is effectively 2 times x plus 2 to the power 38 minus s.